Okay, this is a recording of chapter 19, part 2. So I'm trying to get a complete set of all the videos. Okay, so this is one of those that was missing. Okay, so let's pick up where we left off. I won't do a review because the last lesson was very long and very detailed. Go ahead and watch that. We're just picking up where we left off and we're looking at electrochemistry. So the author redefines electrochemistry to remind us that when we're dealing with electrochemistry, essentially we're dealing with a possibility of a two-way reactions. In one reaction, we have chemicals producing electricity via electrons, right? So these chemicals in the reaction release electrons. When you have traveling electrons, well, a group of traveling electrons as they move generate electrical energy. And then you have the reverse also being true, where electrons don't produce chemicals per se, but the electricity facilitates the deposition or the depositing of chemicals. Okay, so in the forward reaction, you have chemicals releasing electrons or producing electrons. In the reverse reaction, you have electricity facilitating the deposition or depositing chemicals. Okay, the forward reaction tends to be spontaneous. So I have the term spontaneous here because it doesn't require electrical energy, but in the process, it produces energy. Okay, so here's where I was talking about the face-to-face class. They do a lab on this part here, so I will refer to it later on. But once again, let's go through the lesson. Electrochemistry is the study of redox reactions that produce or require electrical current. The conversion between chemical energy and electrical energy is carried out in an electrochemical cell. So in the lab, those of you who are doing this lab, you will be working on a voltaic cell. So in general, the electrochemical cell is broken apart into two types. Okay, so let me take a little detour here. We have the electrochemical cell, and you have two main types. So you have the one that is undergoing a spontaneous reaction. So I'm going to call this spontaneous. And with this one here, at least in the lab, it has two names. It is called either a voltaic cell. This is the more common name. And the other term or name used to describe it is a galvanic cell. Okay. Once again, the setup in these cells here facilitate a spontaneous redox reaction. So we have spontaneous redox reaction. Okay. A reaction in which electricity is produced. I'm going to say here, electricity is produced or a product overall. Okay. On this side here, what we see is the electrolytic cell. And in this case here, what we see is chemicals being deposited on something else, or they're just being deposited in general. So this one here requires electricity to proceed, therefore making this a non-spontaneous reaction. So why non-spontaneous reaction? We defined this in the previous chapter, right? Chapter 18 mentioned if a reaction requires energy to even start, that reaction is classified as non-spontaneous. If it doesn't require energy to start, then that reaction is defined as spontaneous. Okay, so let's go back as we're looking at this. Spontaneous redox reactions take place in voltaic cells, also known as galvanic cells. I already covered that, right? Non-spontaneous redox reaction can be made to occur in an electrolytic cell by the addition of energy. When you're adding energy to a system, that system ceases to be spontaneous because it requires energy to begin. Okay, we're moving on from here. And so those of you who are going to be taking this class on campus, you'll be working with this experiment right here. The first half of the experiment, that will be, I think is J1, right? The first half of the experiment is a modified version of this redox reaction. So I like to call this first half here an all-in one, okay? And I call it all-in-one because you have the full redox. So you have both oxidation and reduction happening in the same container. Now, in the lab, for us to conserve chemicals, because you all know these are hard times, right? Instead of doing the experiment in a large beaker, we do the experiment in tiny, tiny test tubes. So you have a tiny test tube, and you will be required to fill the test tube with some solution, right? So you have an aqueous solution of a metal, and you'll be placing another metal. So aqueous solution, that will be the liquid form. And then you have a solid metal, that will be the electrode. That will be the solid metal, also called the electrode. These will be paired together, and we're trying to figure out if a reaction happens or not. Okay, we're just trying to figure out yay or nay. Nothing complicated. Okay, remember, both reduction and oxidation occur in this test tube. We're not separating the two. So essentially, the reaction going on here is redox. So what exactly is happening? Some combinations will produce a reaction. You'll be monitoring this reaction here over a given time. Some combinations will produce a reaction. Some combinations selected will not produce a reaction. For those that produce a reaction, you will notice a visible difference. So when you look at the before and after, so this will be an example of our before. And what is paired here, you ask? The electrode is zinc strip. That's the metal, right? The solid metal. And then the copper aqueous solution, this is aqueous. And our solution in a liquid state, this is copper. How can we tell it's copper? You see the blue here? This indicates copper ions, okay? And up here, we have the zinc solid. Okay, so what is causing us to see product? First of all, we're able to see a visible change here, which tells us a reaction takes place. For those of you doing this in the lab on campus, you're going to see some kind of sediment or a solid precipitate being made, right? Reaction takes place. How do we know that? Because we see precipitate. And just by the observation of the precipitate, we can conclude this reaction is spontaneous. So how are we making such a bold statement that it's spontaneous? Because there is no outside source of electricity here facilitating this reaction. Just by bringing the two chemicals together, the reaction takes place, okay? So what reaction is taking place, you ask? This is when we kind of go into the details, right? Let me go ahead and see, do I have space? No, I don't really have a whole lot of space. So let me go ahead and erase this here, okay? So all pairings do not generate products, but some pairings do. So later on, we'll figure out what pairings actually generate products. Right now, we're trying to figure out, do the pairings generate the products, yes or no? And then once we figure out the yes, we try to put all the yeses together and ask the question, what about these pairings makes them produce products? And then why didn't the other ones produce a product, right? Okay, let's see what's happening. How exactly is the product being produced? So we're starting off with the zinc solid. So the solid here is somewhat of the initiator of the reaction. Zinc solid, right? They're showing you the solid atoms right here. So this is the atomic level showing you almost a play-by-play of what's going on. So we're going to focus on this one particular zinc atom here because this zinc atom is going to start the reaction, okay? It initiates the reaction by releasing 2 electrons. So the reaction actually happening first is the zinc solid atom goes ahead and releases 2 electrons as it becomes a zinc ion, okay? The ion is aqueous, so the solid will remain in solid form, right? The atom form. And then the aqueous, this is becoming a solution ion. So it becomes a liquid, right? But it's an ion, so it's an aqueous. Okay, now we have to go back to 1411. Yes, I said that. In 1411, we said that in general, when you have an atom compared to an ion, the atom tends to be bigger. So I'm going to draw a circle here representing zinc atom. When zinc loses 2 electrons, the resulting ion of zinc, zinc 2+, is relatively smaller. Why? when I was trying to make sense of this and remember this and quickly, I would say electrons were like pounds. And so when you lost 2 electrons, it would be like losing 2 pounds, right? Now, most likely, if a person loses 2 pounds, you may not be able to tell unless they lose a significant amount of pounds. But with the atoms, when a neutral atom loses 1 electron, we notice it because the size becomes smaller. When it loses 2, we notice it too. Okay. Bottom line, the ion is smaller than the atom because the ion has lost electrons. So over here in the picture, they're showing you the zinc atom. The zinc atom loses 2 electrons. So the atom becomes an ion. They don't really show you the picture here. They show it to you right here. And then it's like they don't really follow along. Listen, I didn't draw these pictures. I'm trying to tell a story. Once the atom loses electrons, it becomes an ion, and the size of the ion is supposed to be smaller, right? So it's supposed to be smaller than what it used to be. In the process, the 2 electrons that are lost travel to the surface. So right here, okay, they travel from the atom to the surface of the metal. How do we know they're on the surface, you ask? I'm going to show it to you in the results, okay? This is the first half of the reaction. The second half is the electrons from here that have now traveled to the surface of the metal are now happy to be taken in by a copper ion. It's almost like the copper ion is like, there are 2 available electrons that nobody wants. And they are drawn due to having opposite charges, right? There is that too. The copper ion is drawn to the 2 electrons. It combines with it. So this is the copper ion here that is drawn to the 2 electrons, combines with it to form copper solid. Okay? So we covered this in lecture before. This producing electrons is oxidation. Consuming produced electrons is reduction. Okay, so zinc is undergoing oxidation in the same container, and oxidation and reduction are yin and yang relationships or reactions. They depend on each other. So reduction depends on oxidation happening to get its electrons. And oxidation depends on reduction happening to use its electrons, right? So we see that the electrons produced here are now used down here, and the cycle is now complete. Okay, and we have a redox reaction. Now, because the copper reacts with the electrons, you can see from here to here, the copper size got bigger, right? Because now the copper ion gained 2 electrons in becoming a copper ion and is somehow affixed to the surface of the zinc because that is the instant where it met the electrons. So in the beaker or in the tester, this is what you will see. As the copper ions find the electrons, they will kind of deposit on the surface of the metal. And then, of course, new electrons come and attach to those copper metals, and then the cycle continues, right? And this continues, and it's happening kind of fast until you have a layer of dark copper deposit. Now, when processed, the copper will look more bronze-like. In the solution here, it kind of looks gray-black, right? But we're forming copper solid from copper solution, and the zinc is the one going to the solution right here. Okay, if you leave this overnight, all the blue from the copper will disappear as the copper ions become copper solid. Okay, so the blue goes away because the blue came from copper ions. And then we start seeing that dark color, which will become bronze, right? When it's pure copper, it becomes bronze. So this should be bronze, right? And so as the copper deposits, it becomes a bronze color because it's now forming copper metal. What happens to this overnight or over a longer period of time? This part here will completely dissolve, and it will dissolve, the zinc will completely dissolve to form solution, right? And that's what the reaction is showing us here. It goes from solid to solution. Here we're going from solution to solid. Okay, once again, I like to call this the all-in-one. Now, the story started here. Somehow over here, the story went from your big zinc atom becoming a zinc ion, and the electrons are somehow traveling down here. The 2 electrons are here. They combine with a copper ion, right? That becomes a copper atom. So it's an ion here, Cu2+. here it becomes an atom. Remember, as the ion gains electrons, it becomes bigger because it's like it gained 2 pounds, versus when the atom loses electrons, it becomes smaller as it becomes ions. Anyway, let's go ahead and move on. So we mentioned before that voltaic cells or galvanic cells, these tend to be paired with spontaneous redox reactions. Okay, so what if we want to harness the electricity? Remember that, well, this is my point of view. I try to interject my point of view in understanding chemistry or science or the world around me, period. I feel like as scientists, we're usually trying to find out what is in it for us. I mean, when I say us, I mean humans, right? As we observe the redox reaction here in the all-in-one container, the great thing about this is we're able to observe the redox reaction. The not so great things about this reaction here is we can't really get much of value just by looking at this. I mean, I guess if you want to deposit copper, you have established that. But what if we want to harness the electricity generated in this reaction? If that is our goal, then what we want to do is actually separate the reduction from the oxidation. So I'm going to draw a picture of what I need, okay? Because I was trying to copy the other picture over, but it wasn't working. Remember, we're dealing with an all-in-one setup for experiment, right? For most electrochemical cells, the reduction part and the oxidation parts are separated, okay? And then for most, not 100% of the time, but for most authors, the oxidation part is kept on the left side, and then the reduction part is kept on the right side. Since I'm detouring as I illustrate this to you, for those of you completing J1 lab on campus, the second half of the experiment that we work on in the lab has the oxidation and reduction part separated. Why would we want to do that, you ask? Most of the time, if we have a goal of measuring the amount of energy, measuring the voltage is the amount of electrical energy generated.
So in general, the oxidation part of the reaction is put on the left most of the time. So I'm going to draw a container here. And this time, instead of doing an all-in-one setup, we will have two beakers. One will represent the one half of the reaction. And by the way, the oxidation part is called a half cell reaction or a half reaction, indicating the oxidation is one half and reduction is the other half. So the two halves together make the whole. Okay? Oxidation part here is the part where electrons are produced. Okay? So this is called the oxidation site. This also has a general name called the anode. Okay? And then the site that is the reduction site is also called the cathode. So when I was in school, I learned about a red cat. I heard somebody say red cat, red cat, red cat, and I thought it was a literal red cat. I tend to be a literalist sometimes. You know, when I'm having my moments, I'm like, where is a red cat? I don't see any red cat. And they said, no, reduction cathode. I was like, oh, red cat. That's a way to remember it. In the reduction site, which is normally on the right, electrons are consumed. Okay? What else? So before I add more to this, let me go ahead and take what we had here. We said oxidation was happening with zinc, right? So when you're setting up the oxidation site, the best way or the easiest way to do this is to match the electrode or the solid metal to the solution to prevent them from reacting. We are not trying to repeat the all-in-one situation we had going on here, right? We're trying to make sure the reduction part and the oxidation part are happening in two separate chambers. So they're not exchanging electrons without our involvement, right? So we have oxidation once again on the left side. Pick a solution here that has zinc ions in it. So we'll call this the zinc ion solution. So they won't mess around and exchange electrons between each other.
Okay. On the reduction side, trying to pair this or make this similar to what we had in the all-in-one situation, we have our copper here, and then we have our solution of copper ions. So Cu2+. Okay. Now, as the reaction proceeds, we went back here and we said, for every cycle of the reaction, 2 electrons are generated, right? How do the electrons then get to the reduction side? The electrons generated this time will not stay on the metal surface, right? or the electrode surface, they will actually travel through a wire. So I'm going to make this a voltmeter. They will travel here because the electrode conducts electricity, right? And then travel all the way through an external wire to the voltmeter and travel all the way to the reduction site. Okay. So what we're showing here is the flow of electrons. So electron direction. This is the flow. So electron flow direction. Wait, let me write this better. I can do better. Electron flow direction. It's flowing from the oxidation side to the reduction side. Okay. So before I finish the story, what causes the electrons to flow? Just because we said oxidation is left and reduction is right. Not necessary. Let's detour back to physics. Okay. In physics, we're told in general, objects tend to travel from higher gravitational potential. So this is higher gravitational potential to lower gravitational potential. Just saying that if there's an object that is somehow elevated from the ground, because the position above the ground has a higher potential energy or a higher gravitational potential energy, the object, when released, will fall to the ground, to the area that has a lower gravitational potential energy. I wanted to make sure I said this right. Bottom line, objects tend to move naturally from higher potential energy to lower potential energy, right? And with this trend that we see here, this also plays out when we're dealing with the flow of electrons. So the question is, how is one higher over the other when they're at the same level? We're not dealing with gravitational potential energy here. Here we're dealing with the potential energy called the voltage, right? The volt difference. So the oxidation side tends to have a higher potential compared to the reduction side. This tends to have it's all relative, right? Lower potential. Okay, so before I move on, for the ones that were selected in the lab where the reaction didn't take place, it's just because these were switched. The one with the lower potential was placed to the left, and the one with the higher potential was placed to the right. Okay. And so, of course, when you do this in lab, you will see how it works out. It's important for the higher potential to be the oxidation and the lower potential to be the reduction. The difference in potential is what causes the electrons to flow from the oxidation side to the reduction side. There's another reason. Oxidation sites tend to be more negative, and the reduction sites tend to be more positive. So I'm trying to tell a difference as I tell you the story. So oxidations here are usually relatively more negative. Okay. And the reduction side is more positive. Now, when I was in school, I was like, I will never remember this. This is too many details, right? So when I feel like I'm not going to remember something, I try to anchor that information to either my life experience, or if I can't find one, then I try to create one by making up a story, right? And then the story becomes my go-to. So here, the story I remember was when I was sick. My dad is a teacher, and when I was at home in elementary school, sometimes I'll get sick and I'll stay home. And oh my goodness, his standards are so high, and they were so high compared to my teachers. My teachers were more laid back than him. So when I stayed home when I was sick, he will make the home environment for me, this is my perspective, so negative by being like, oh, where's your homework? Have you done your homework? Da 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 da. Why is this way? And then he wants me to go and review everything and study. And I was sick. I wanted to live my getting well life at home, relaxing. So I feel like he made the environment home so negative that I actually preferred to stay at school when I was not feeling well, because I was like, at least the teachers will feel sorry for me here and not ask me to do all this extra work, right? Somehow he just made us do a lot of work at home that I just felt like it was a negative environment. So why do I bring that up? When the electrons are here and they generated here, the environment they generated in is negative. So there's actually a repulsion. There's a repulsive force that pushes the electrons away from the environment towards the more positive environment. So the electrons are drawn to the more positive side because opposites attract. So for in my backstory, school compared to home was positive. School was like the reduction side, while home was like oxidation. Because I was like, I don't need all this negativity. I'm just gonna go to school tomorrow, you know? Yeah. So the electrons, once they're generated, are drawn to the positive side, away from the negative side. So there's two things at least causing the electrons to flow. Okay. Now, electrons only flow as long as the right side is positive, the left side is negative. Okay. If the left side becomes less negative, guess what? The electrons stop flowing. To keep the electrons flowing, a salt bridge is introduced. Very, very important. Okay, my picture isn't the greatest. Don't judge my picture. This is called a salt bridge. What is the purpose of the salt bridge, you ask? It has a very important purpose. Its purpose is to keep the negative side negative while keeping the positive side positive. For every one negative charge that leaves this environment here, a negative charge comes in to replace it. The more common chemicals we have in the salt bridge is essentially a potassium nitrate salt bridge. Nitrate tends to be negative and then potassium is positive. So the nitrate will flow into the oxidation side to replace the electrons lost. It cannot do the job of the electron by moving across this way, but it comes in the solution to keep this environment here negative. Does that make sense? So electrons are lost, and then, of course, for every one electron that leaves, one nitrate comes in. Since zinc produces two electrons, two nitrates will come in to replace the two electrons lost, right? As the reaction goes along. On this side here, we mentioned on the reduction side, you have two electrons coming in and taking copper 2 plus out of solution. So we're having less and less positive ions in the solution that was already present, right? These get consumed, so we have less and less of these. So we need to replenish the positive ions that are being lost. So on the other side here, you have potassium ions going into this solution here to replace the copper ions being lost. So for every one copper ion that gets consumed, two potassiums come in to replace the copper ion. So this side remains positive and does its job of pulling in the electrons. Okay. Okay. So we have a salt bridge, and so oxidation here, and ions from salt bridge are drawn to this site, right? Because they're replacing electrons, And then here you have cation from salt bridge are drawn to this site, replacing the cation in solution. Okay. Okay, so let's go ahead and move on. Remember, the force that drives the electron out from the oxidation to the reduction is called electromotive force. And that's because of the voltage difference, right? So force driving out electrons is called the electromotive force. Okay. And that's what pushes the electrons from the left to the right side. Usually, of course, I think this is 1.1 volts when you work everything out. Okay, let's go ahead and move on. I feel like I just went on this backstory, but remember, this allows us to measure the voltage between the two sides. And if we want to, we can harness the electricity here and do something with it. We can only do that because we separated the oxidation from the reduction versus this all in one setup here where you can't do that. Okay, you can observe, but you really can't harness electricity. Okay, so the importance of separating once again is to harness electricity as we continue to observe the changes. To generate electricity, essentially what happens is the electrons that are produced on the anode side or the oxidation side travel through a wire. As they travel through a wire, you have the charge passing through a wire, passing through a particular point over a given period of time. That is essentially electrical current, okay? And it measures once again, our electrons are flowing through a wire, or electricity can be generated by ions flowing through a solution, right? But our focus tends to be the electrons flowing through a wire over a given period of time. Okay, we mentioned this before. So redox reactions involve the movement of electrons from one substance to the other. We've seen that it's usually from the oxidation side to the reduction side, right? And because of that, redox reactions have the potential. I mean, they have the ability, let's not overuse the word potential here, to generate electrical current. When you have a spontaneous reaction like the one we just looked at right now, spontaneous redox reaction, it does not require the use of external source of energy to proceed. Therefore, it's spontaneous. Therefore, delta G is negative, okay? What we just saw was a voltaic or galvanic cell. It does produce electrical current from a spontaneous redox reaction. And as it says right here, for us to use that current, we want to separate the place where oxidation takes place, called the anode, from the place where reduction takes place, called the cathode. Okay? And I mentioned to you that the whole setup is called the electrochemical cell. The left side is usually the oxidation part. The right side is usually the reduction part. And these are half of the whole. So the oxidation side alone is one half. The reduction side alone is the other half. As long as you keep them separate, I mean, you're still connecting them via the wire and the salt bridge, right? But that allows you to harness electricity. It says right here, this is kind of repeating. Electrons flow through the wire, ions flow through the salt bridge, replenishing whatever has been lost, negative or positive charges, right? The flow of electrons require a conductive solid material, right? We need that electrode for the electrons to flow from the oxidation site. That's very, very important. And what else? I'm trying to hit the key parts. And you want to make sure, once again, to keep the negative side negative, the positive side positive by using a salt bridge. That is required to replenish the lost electrons on the anode side or the oxidation side, and then the lost ions on the reduction side. Okay. So I gave you guys my own little list. It's telling you here the anode is a negative potential. So when you have a battery, I'm going to draw this a battery like this. When you have the outy part of the battery, that tends to be the positive side, right? Then you have the negative side right here. This is what tends to be the negative side. So this would be a anode right here, and then here you have the cathode side. You just like to draw this little picture here. Sometimes I think the batteries appear like this, right? Where you have the cathode side and then the anode side is over here. Anode. You get it though. The anode side is a negative potential. That's the part, the electrode where oxidation occurs, and ions from the salt bridge are drawn to it to replace the electrons that were lost. It tends to be connected to the positive end of the battery in an electrolytic cell. So in an electrolytic cell, this tends to be the opposite, right? I won't talk much about this right now. We're not really doing this in the lab that much, so it's just casually mentioned. In the cathode here, the cathode tends to be the opposite side or the right side. This is where you have reduction taking place. Oh, anode is where you have oxidation taking place. Oxidation. I like to write it out, even though it's said right here. Reduction occurs in the cathode. It's the positive terminal, ergo red cat. Cations from the salt bridge are drawn to it because that's where cations actually react. And then this tends to be connected to the negative end of the battery in the electrolytic cell. Okay, so we'll cover that part here later on. I already told you about this voltaic cell. As I said right here, we're separating the two so that we can see, we can actually harness the electricity being produced. You see the flow of electrons from the oxidation side to the reduction side. Their pictures are way better than mine. But you can see what happens here. You have a metal atom that's bigger, forming a smaller metal ion. In the process, it loses 2 electrons. The electrons do not stay on the surface here like we saw in the all-in-one container. They're actually pulled by this invisible electromotive force, right? The electrons are pulled here together and they travel through the wire like the bulb. Keeps going over here, and then they're drawn to this end because this end is more positive. This end they left was more negative. And when they come here, they don't go into solution. They stay on the surface of this metal. And then the ions from the solution are drawn to the electrons. Look at the electrons over there. And then they deposit here. So as the reaction proceeds, this electrons erodes as it gets smaller and smaller and smaller because this solid is going into solution, right? While on the right side, this gets bigger and bigger and bigger because you have the ion from the solution depositing on the electrode. So this gets larger. I didn't mention that before. As this gets smaller, so I need to go back and add that to the list, right? I'll add it to my list since I wrote on my list. I forgot to mention that because it's not really mentioned here. It's implied as you go through the experiment that oxidation side electrode with time gets smaller, and then the reduction side electrode gets larger, okay? And you get to experience that as it gets, because it's depositing, while this one here is dissolving. I don't want to say eroding, but it's dissolving, right? You have the atoms converting to cations and releasing electrons. So the metal that produces the ions gets smaller and smaller and smaller as it makes more ions. Okay, where are we at? So we made it down here. We made it to the picture. Okay. So like before, everything is started on the oxidation part where 2 electrons are generated. They travel over and then everything culminates, right? It ends with the reduction side. That's just one complete cycle, but this cycle keeps going on and on. So you have like the first cycle, zinc produces zinc ions, releasing 2 electrons. The electrons travel to the other side, the reduction side. The electrons are then consumed by copper ion and then produces copper solid that deposits. Okay, so the lost electrons are replaced by nitrate ion. As the cycle continues, the lost copper ion are replaced by potassium ion as the cycle continues, and then the cycle continues on and on until somehow this stops being negative and this stops being positive, and the reaction is over, right? When there's no need for the electrons to move over, or somehow you run out of chemicals, if this completely dissolves, the reaction cannot continue, even if you have a positive and negative, right? A negative or positive. If you ran out of the anode, the reaction stops. The difference that causes the electrons to flow is called the potential difference, right? And that's what causes the electrons to flow from one end to another. And they're flowing from a high potential to a low potential. For right now, I'll say, remember, the electrical energy being produced here is measured in volts. And 1 volt is equal to 1 joule per coulomb. You want to write this down because you're going to need this down the road when we're trying to measure the Gibbs energy. Gibbs energy is measured in kilojoules, so we need to convert the joules here to kilojoules. So we need to remember that 1 volt equal 1 joule per coulomb, okay? And then the coulomb is a unit for charge. Of course, joule is a unit for energy. Electromotive force is that invisible force that is pushing the electrons away from the anode towards the cathode, okay? As we measure the electromotive force, we are also measuring the EMF of the cell that will be symbolized by E naught standard because it's measured in standard state. And of course, that will be for the whole setup, okay? Remember, the moving electrons generate current, and the current, which has a symbol ampere. As you're measuring current, which we don't do a lot in chemistry, but if you're going to do this in physics, it's usually measured in ampere. and 1 ampere is equal to 1 coulomb per second. We will need this for the last question in this chapter, okay? So we're being told a very important thing here. The electrode surface contributes to the amount of electricity produced, right? Because remember, as soon as this runs out here, we can't make any more electrons. So the bigger this is, the more electrons you can generate. Because imagine each atom released from that big electrode produces electrons. And then, of course, it facilitates what's going on in the reaction. So the size of the electrode influences the number of electrons produced. Okay. So where was I? I think I've gone too far. Yes. The larger the electrode, even in a battery, the more electricity is produced. And later on, we'll see that the concentration of solutions matters too, because they all contribute to what's going on. No pun intended, right? If the anode electron is large, it contributes to the amount of electricity produced here by making more electrons. If the solution has high concentration, you're increasing the amount of cations, right? Which of course helps the cycle to continue. So there are all these factors that can contribute to the voltage. Anyway, I feel like I'm getting ahead of myself. So one of the things we're going to be measuring, especially in the lab, those of you who are doing the lab, is the cell potential, right? The EMF of the cell, electromotive force, or on a practical note, the voltage of a battery. Now, I remember taking a physics class where we discussed voltage, but our goal was to amplify voltage, right? To make it bigger. You could attach batteries in series or in parallel and all that stuff. What we're trying to figure out here is making the voltage to begin with, creating the voltage to begin with. So we're going to be measuring the cell potential under standard conditions. So we have to define standard. Remember, standard is kind of like organic or kosher. It just means when you say a meal is kosher or organic, it is understood. I think organic may be a little bit more loose, but kosher tends to be more strict. When you say meat is halal or kosher, it is understood that the meat was prepared under very strict religious conditions, right? When it comes to the experiment that has this signal right here, the standard condition, this experiment is done under understood conditions, which are known as standard conditions. What are these understood conditions? The temperature has to be 25 degrees Celsius. If you're dealing with the pressure has to be a pure gas with a pressure of 1 atmosphere. If you're dealing with a solution, to get the numbers they got, the solution has to be a 1 molar concentration. So shout out to my student Josh, who actually noticed that the solutions we had in the lab were not 1 molar. When I get in the lab, I'm in a hurry to try to make sure everybody can get stuff done so that we can do the post lab. And then he pointed out, hey, because I kept saying, when we get to lab, you will notice our solutions are 1 molar. Well, they weren't 1 molar. So our voltages that we got in the face-to-face lab did not match the theoretical. Go figure, right? Because for us to, let me kind of fast forward a little bit so you understand what I'm saying. For us to get numbers that match the table, this table shows you the potential for the half cell reactions. So for us to get numbers anywhere close to these right here, we have to follow standard condition, right? So in our lab, well, we didn't do that. So we're going to have a chat. Well, we might be switching the lab anyways, but in the new lab, I have to request, can we please make these solutions as 1 molar? When I read through the lab, though, in their defense, no concentration was mentioned. So kind of implying that there was some leeway in that. But if we want, remember, standard condition is trying to say, you want to repeat the results we got? You got to follow our conditions. And our conditions are standard. And these are, you have to have a pressure of 1 atmosphere, 1 molar concentration of solution, okay? And then what is the EMF of the cell, the E naught of the cell? It is the sum of the potentials for the half reactions. So while we are here, we'll be told at some point that the E anode, the potential standard of the anode, is equal to negative E of the cathode, okay? Now, while this is true, I just feel like sometimes this can be a little bit complicated or a little bit confusing. So when it comes to finding the potential of the half, I mean, sorry, the potential of the cell of the overall reaction of the half reaction at standard state, we just take the potential at standard state of the cathode minus the potential of the anode. We will go with this formula here so we don't have to subtract or add anything or modify anything. When we go back and look at the table I showed you before, we will copy the numbers as is, okay? The table I showed you here, we will use the numbers as is. We will not have to modify these numbers, okay? Okay, let's go ahead and make some progress here. So I've already told you guys about all this stuff. Yeah, so I won't repeat this. What I want to talk about is the cell notation. I told you all earlier that my hypothesis is chemists are hardworking, lazy people. They work hard with the chemistry, so they try to use shorthands wherever they can to preserve brain energy. What I like about the shorthand notation is it describes the voltaic cell and it's written using the following format. You tend to write the solid electrode first, or the electrode. It doesn't always have to be a solid, but most of the time it is a solid, unless it's some kind of gas, and they'll tell you that. And then you have the electrolyte, usually an aqueous solution, right? Related to the electrode. And so you put the symbol here, the elemental symbol of the electrode, the ion symbol. So this is the element symbol of the electrode. Of course, you want to put this physical state. You put the ion symbol of the electrolyte. Don't put the whole, if it's like copper sulfate, just put ion. That is important in our reaction. And then you have this vertical line here. The first vertical line, the single vertical line, indicates the phase barrier. Just saying that the chemical on the left and the one on the right are at different physical states, right? From solid to aqueous. They're going to look different. They're different physical states. Then you have the two vertical lines. This is showing you that you have crossed from the oxidation side to the reduction side. So that indicates the salt bridge. Okay, so it says right here, indicates the salt bridge, and then it also indicates you cross from one side to the other. What I like about the cell notation, the side on the left usually goes with the anode. And then the side on the right usually goes with the cathode. Not all the time, but most of the time. Okay, so what do we have on the cathode? We have electrolyte again, aqueous. So it's kind of like a palindrome, right? Or a mirror image, not really, but the format is similar to what we had in the other side, but the reverse order. So you have aqueous first and solid second. Okay, those of you who are working on the lab J1 lab, when you get to the lab, you will see the shorthand notation and it will look something like this. And you can use this shorthand notation to build your setup because it tells you what has to be on the left side. Well, what is usually on the left side, what's on the right side, and it tells you what the components are. Find the electrode, usually solid form. Find the solution, usually the ion. For the anode, that'll be the left side. Of course, you want to connect these two because they are connected. And then find the electrolyte for the right side, the reduction, and then the electrode. Okay. For the one that we looked at earlier, this is pretty much, it has to correspond with this, right? This was the oxidation side, and then this was the reduction side, reduction. So you can see how that plays out. Is that consistent in the picture? Yes, it is. Oxidation side, reduction side, okay? I have explained this so I can move on.